Hi there, my name's Shane Windsor and I'm a lecturer in aerospace engineering at the University of Bristol. And welcome to our workshop on Would Planes Be Better If They Were More Like Birds? And welcome to the Flight Lab at the University of Bristol, where we work on developing aerospace technologies such as unmanned air vehicles, as you can see on the walls behind me, and also studying the biomechanics of bird flight to get inspiration for developing better technologies for aerospace applications. And I'd like to introduce the team of people involved in this work. So here in the Bio-Inspired Flight Lab, we've got a great group of researchers and PhD students. And we've been working closely in collaboration with the Structure and Motion Lab at the Royal Veterinary College. You can see them here with their birds. And also, you can see Lloyd and Rose Buck. These are professional bird handlers who we work with, and they have amazing birds of prey that you're going to see a lot more of in these experiments I'm going to tell you about today. So, as an aerospace engineer, why am I really interested in bird flight? Well, it's because how good birds are at flight, how amazingly elegant, efficient, and robust their flight is. Birds can fly in all weather conditions in ways that currently our current small-scale unmanned air vehicles would really struggle. They're also very efficient and have very efficient long-endurance flight under these rough, gusty, turbulent conditions. And these are all things that we would like to improve on our aerospace technologies, whether they be small unmanned air vehicles or large manned aircraft. So, this is Moses. He's a peregrine falcon that we work with, and we're asking him to fly past an array of cameras here. And you see he can fly very quickly and then very precisely as well. So here we see high speed of video coming in to hit a lure. He's suddenly doing these large dynamic wing braking, morphing motions and very precisely hitting the target. So let's take a look at some of the sort of vehicles that we'd like to have that same flight performance that we see from Moses. So you might recognize vehicles like this. This is a quadcopter or a drone, and this is fantastic for when you want to hover and get right up close to things. For instance, we use them for taking video footage of bridges, so we can inspect them for damage and see if they need any repairs. And so these are very difficult to get to places normally, but with a quadcopter you can get right in there and have a closer look. However, the problem with these rotorcraft is they generally don't have as long an endurance or as range as you might like for some jobs. And in that case, you'd like to use vehicles more like this. So this is what we call a flying wing, and you can probably see from why it's called that. So it's generally one large wing. In this case, we've got a prop at the back. And these vehicles have really good endurance and range. And we use vehicles like this for doing jobs like sampling the gas coming out of the top of an active volcano. So in that case, we want to be able to launch from a long way away where we can safely operate, have the vehicle fly for miles and miles to the top of the volcano, take a gas sample, and then fly back. So if you're interested in kind of long endurance or long range work, then you want to use a fixed wing vehicle like this. Or if you are wanting to do both, then we have vehicles that look like this. So this is a hybrid with multi-rotors. You can see some at the back here in the front. Can take off vertically. And then also, once it's in the air, these motors can rotate around and it can fly as a fixed-wing aircraft and get that long range and endurance. So we're starting to see lots of novel and different configurations for our small unmanned air vehicles. We're also interested in novel, different types of aircraft for manned aviation as well. And here are some examples. So I was talking about a flying wing. The bottom right image is a flying wing, but one that could carry hundreds of passengers. And it could be more efficient and potentially even be electric powered. And that's what we're showing also on the top right, is a concept for a long-range, more fuel-efficient aircraft. You see it's got these long, high aspect ratio wings and strut bracing. So fuel burn and efficiency and the move to more electric aircraft is on the future. We've also got really different, novel concepts for aircraft, like the images in the middle and the top left. These are what they call urban mobility or personal transport aircraft. These are basically scaled up versions of the quadcopter I was showing you before that can carry people. And the idea is that these could be used in the future as air taxis. You dial it up on an app on your phone, one comes and lands outside your house, you jump in, and then it takes you across the city and lands outside your destination. So, these are the concepts that we're thinking about in the future. But there's currently a lot of challenges around how to operate these future vehicles as well as current vehicles in gusty, turbulent conditions close to buildings potentially, and also questions about fuel efficiency and reducing the energy costs of flight. And this is an issue for both manned aviation and for these small-scale vehicles as well. And what we want to do is look at potential solutions to these problems. And this is where bioinspiration can come in handy. So the idea of bioinspiration is that we look at natural systems, in this case birds, and look at the principles behind how they're adapted to overcome these sorts of challenges. And then take that understanding of those principles and apply them into developing inspiration for new technologies. And so that's what we're going to be telling you more about today. Now I'm going to introduce Jonathan Stevenson, who's a researcher who works with me, and he's going to tell you about one of the projects that we're working on. Jonathan.
Thank you, Shane. My name is indeed Jonathan. I work here in the Bristol University Bio-Inspired Flight Lab, where we build these new and exciting experimental aircraft. Today we'll discover two ways that birds could help us build better aeroplanes. First, we'll see how they use their tail for super smooth, efficient flight, and then how they use their wings to shrug off those pesky gusts, the kind you get on a blustery day. But first, I want you to imagine an aircraft sitting on a runway. What do you see? Well, there's a long tube called the fuselage, which carries the passengers and the cargo. You see a wing on each side, one right, one left. They produce the upforce, or lift, that actually holds the aeroplane in the sky. There are the wheels, of course, below the aircraft that keep it above the runway and allow it to land softly and smoothly. But at the back, there is a tail. What does the tail do? Its main job is to provide balance and stability in flight. And without it, an aeroplane would be very difficult to fly, if not impossible. It also helps with maneuvering, and all of these things are true for aircraft big and small. Now, it might surprise you to know that most aircraft actually produce downforce with their tails, not upforce or lift like the wing. And that means that the wing and tail are actually fighting against each other some of the time, which seems inefficient. If you want to keep the aircraft in the air, surely all of the aerodynamic forces should be pointing upwards. Well, we as researchers wondered whether birds fly in the same way. Do they use their tails like aircraft tails? And we decided to design an experiment to test that hypothesis. Our friends and collaborators at the Royal Veterinary College near London have a very large lab where we can fly birds and see exactly how they do it. We filled the lab with a cloud of tiny soap bubbles, each one filled with helium so that they hang or float in the air. Now, these bubbles will do whatever the air does. So if you swish your hand through them, for example, the bubbles will churn the air and allow you to track the motion. So with the lab set up, we invited a selection of birds of prey to fly down through the bubble cloud to see exactly how their wings and their tails produce aerodynamic force using the air. And that is what you can see here on these magnificent videos. In particular, take notice of the swirls and the vortices that are shed off the wingtip as the bird glides through. These vortices actually tell us the direction of the force that the wing or the tail is producing. Now, we know the wing must be producing lift because the bird is staying aloft. And in that case, the vortices rotate inwards, in other words, towards the body. And you can see that here on the animation. The blue bubbles are those going down, and the red are those going up. What does the tail do? Have you spotted it yet? Well, I will reveal the real answer very, very shortly, but first, let's have some fun and build our own gliders to see just how important the tail is for balance and stability in flight. I'm going to show you how to build a paper glider that demonstrates the principles of the tail. We have a copy of instructions here that are available through the University of Bristol's website. And you will need a blank sheet of paper to make the glider. You'll need a pair of scissors. You will need a ruler. And you will need a pencil or a pen. First stage, step one, is to make a fold along the length of the paper. And you can crease the paper sharply. Then unfold. Next stage is to make fold across the width. And then unfold. And you're going to flip the paper over and draw a line 1 centimetre from the top edge of the paper. So I'll just make a couple of construction marks, 1 centimetre in. Okay, and once you've done that, flip the page back over and fold a strip from the top edge to the line. Use the line to judge how far to fold the strip. Okay, that runs along the whole top edge. Now we're going to keep folding that strip end over end on itself until we reach the center of the page. So just keep going. Going to need you to do it several times, but you should get soon to the center. And once you're there, you can stop. You can then fold the aircraft or the glider back in half. Mark out some construction lines. The first is 5 centimeters from the bottom edge. We're on step 5 of the instructions for anyone following along. We then draw a construction mark 2 centimeters in from the left edge and another one 7 centimeters in from the left edge along the bottom side. We're going to join those 2 construction marks with a straight line, and that marks out the tail. Okay, we're now going to cut along the diagonal and the horizontal line, being careful not to go too far and chop through the tail. That's the first. Make sure you cut through both layers of paper. That's the second. Unfold the glider. And now we're on step 7. I'm going to mark out lines for the tail tabs. The first thing I like to do actually is to mark a center point here, just using a fold, and then either side we will mark out 3 centimeter tabs. And these need to be 1 centimeter deep, so we'll score those off the other way with a ruler. It's worth spending a bit of extra time getting this right, because we're going to cut along these lines and we don't want to cut too far. All right, so you should end up with that. As I promised, we're going to cut along them, so very carefully cut along the line to the end without going too far. And there you have it. That's the finished glider. Now for the first flight, we're going to bend the tabs downwards. Okay, we'll give them a sharp bend downwards. You can crease them if you like, but a sharp bend is all that's needed. So you should look like that. Let's see how it flies. And you don't throw it too hard. Just need to give the glider a gentle push. And notice what happens. Takes a nosedive towards the floor. I will confess that that is a setup. We've set you up for failure there. The point here is to illustrate just how important the tail is for balanced flight. I'm going to try another flight this time with the tabs bent upwards, and you will see a huge difference. Okay, that's with the tabs bent upwards. And notice how differently this flies. Sails through the air with ease and grace. So now we've seen for ourselves just how important the tail setting at the back is for balanced and stable flight. We're going to return to the birds now and ask that question once again, what is the tail doing? Well, I told you that the wings produce lift and the swirls that are generated at the wing tips rotate inwards. If you look very, very carefully, you can see that the tail behaves and works in the same way. In other words, the swirls it produces also act inwards, so it too must be producing lift. That's particularly clear on the animations here, so just watch the blue bubbles at the center. You'll see they're thrust downwards. And they start to rotate inwards. So birds' tails produce lift, just like the wings. Now, it wasn't what we expected, given how aircraft are usually set up and designed. This means that birds fly differently, and what they compromise in stability, they gain in agility and efficiency. And this is a principle that we could apply potentially to aircraft like the ones you've already seen in future for a more efficient and maneuverable flight. We're now going to switch gears and see how birds use their wings to deal with gusts and turbulence. We're doing collaborative work with the Royal Vet College to try to understand how birds respond to disturbances in their flight, particularly gliding flight.
What I'm really interested in as an aerospace engineer is how birds deal with these complicated, really gusty, difficult to fly in conditions and how they do it so well.
The idea is we can use these experiments to understand and then extract inspiration for the design of unmanned aerial vehicles of a similar scale. For this experiment, we constructed a bespoke gust tunnel, or gust generator as we call it, which is a device that throws gusts of different speeds at the birds as they glide down our setup.
The way birds cope with that is to change their wing position and their wing shape, and the same for their tail, so that their head remains stable and they fly nice and smoothly despite very gusty conditions. And it's those movements of the wing that we're aiming to capture with 14 high-speed cameras and 10 motion capture cameras, which really capture every detail of every feather as they buckle, bend and are moved throughout these manoeuvres.
We get lots of different views from different angles, and with all those different views we can work out the 3D shape of the bird when they're flying. Once we've got that 3D shape, we can use it to generate 3D printed models like this one. So this is a small 3D printed model of Lily's exact shape in flight. We can also print larger models which we use for wind tunnel testing, where we can test other things that we can't do with the real birds.
Well, we've probably nearly all taken a flight which has suffered from turbulence. And part of the reason that it is unpleasant is because the aeroplane doesn't really respond in a particularly fast or practical way to reject the gusts that it's experiencing. Birds, on the other hand, are very good at doing that. The idea is that we learn from the birds about how they shape shift their wings.
And take our understanding of what the birds are doing and then see if we can use that to improve the flight control of our small unmanned air vehicles.
Then we might be able to get more agile flight, smoother, more comfortable flight, and probably fuel economy benefits as well.
So, we asked the question, what happens when birds get hit by a gust of wind? And that was the big experiment that you've just seen. So, what was the answer? Effectively, the bird's wings are acting as a suspension system. You would have seen that they were flying along and suddenly they got hit by a gust of wind. The wings went up, but the body continued in a nice straight line. So the wings are acting just like the suspension system of a car. They're absorbing the sudden change in like the road surface or the gust and not transmitting that into the body or into the cabin, as is the case with a vehicle. So we've got a suspension system which is working aerodynamically in flight. And we wanted to understand the physics a bit more about how that happened and how it worked. So we built this model that you can see in front of me. It's a wind tunnel model, and it is meant to simulate some of the aspects that we think are important about what the birds are doing. So this wing is on a carriage. So the carriage can move up and down. So it's just like the fuselage of the aircraft or the body of the bird. It can move up and down, and we can see if it's getting knocked by the gusts. The other aspect we have of this wing is that it's joined to the carriage with a hinge. This is just like the rotational degree of freedom at the shoulder of the bird. So we've got a hinge here where the wing is hinged and can move freely up and down, or rotate up and down, and also move up and down with the carriage as well if it needs to. So we put this in the wind tunnel and we turn on the wind. And the wing produces lift and it lifts up the carriage, and basically it's flying in the wind tunnel. And then we send gusts of wind down the tunnel and see what happens. Now, exactly what response we get depends on where the gust acts on the wing. All right, so what happens if I hit it near the shoulder? If the gust hits near the shoulder, you'll see it suddenly knocks the fuselage up, the carriage moves, the bird would move up. So if we have the gust acting at the shoulder, we get, or close to the shoulder, we get this vertical upwards motion. What happens if the gust or the center of pressure is right at the wing tip? So now here we get a sudden gust. You'll see the carriage doesn't move as much, but if you watch carefully, it would actually, you can see it moves down slightly and before moving up again. So you get this initial response where the carriage goes down or the body goes down. So if we have it at the wing tip, the gust makes the body go down. If we have it close to the body goes up. So somewhere in between, there must be a point where the body goes neither up nor down. And this is something that's known as the center of percussion. And you might be much more familiar with it from sports. So sports where you use a bat or a racket like cricket or tennis, if you hit the ball really nicely in the center of the bat or right where you're aiming for, you hit the sweet spot. And this is the spot where it feels really nice when you make a connection. You don't get any juddering or kind of force going back through your hand. It feels nice and clean. And that's where the center of percussion is. When you're hitting the ball right in the sweet spot of the bat or the racket, this is the center of percussion. You don't get that juddering of your hand getting pushed back as you hit. It's just a rotation kind of motion as you swing through. So this is a sweet spot, and a wing will also have a sweet spot as well. And we'll see if we can find it. So here, now if I'm going to hit the gust onto the wing at its sweet spot, you'll notice the wing just rotates and we have practically no motion up or down of the carriage or of the body of the bird. So when the force of the gust acts at the center of percussion or the sweet spot of the wing, then you just get a rotation of the wing without the body getting knocked up or down. And this is exactly what's happening with the birds. Their wings are shaped in such a way that the center of pressure, the lift produced by the gust, acts at the sweet spot or center of percussion of their wing, and the wing just rotates without their body being knocked up or down. So, and that creates this suspension effect, which gives the bird time to respond to the gust and then do later slower corrections to keep it flying nice and steadily. And we can apply this in aerospace systems. So here's a simple foam glider that we modified to have a hinge. And the one on the left you can see here has that hinge. And you'll see it doesn't get knocked up as much as the one on the right, which has a fixed wing. So even with this very simple implementation of a hinged wing, we can see that this aerodynamic suspension effect works. You've got the wing being able to rotate around the shoulder, and the mechanics of the system are such that the body or the fuselage of the aircraft doesn't get knocked up as much. So, to summarise, we've learnt two things today. Firstly, we've looked at the tails of the birds, and we find that they use them differently from aircraft. They're using their tails to produce lift, and this means that they can fly more efficiently and use less energy. And they're more agile. But the trade-off is that they're less stable, and they're always having to actively move their tails to keep control of their flight. The second aspect we've learnt is that the bird's wings are acting as a suspension system, and that by rotating around the shoulder, they're able to reduce the effects of gusts on their flight path and keep a smoother, steadier flight. So I'd just like to thank everyone involved in this research and the organisations that have made it possible, such as our funding agencies and the support of our universities. And I'd just like to thank you very much. If you'd like to learn more about the engineering aspects of what I've spoken about today, you can visit www.bristol.ac.uk Engineering Outreach. And there you'll find newsletters, additional workshops and other resources. If you're interested in the biological sciences side of things, you can look at the RVC's website. They've got some great newsletters there which talk more about their research and about biological science and veterinary science in general. Thank you very much.